I hope you all are doing well. Welcome to Unit 3 of STA 220. And Unit 3 is all about what we call shape, center, and spread. And so we've already talked about the shape of a distribution a little bit. So we've talked about how things can be symmetric, or maybe a graph is left skewed or right skewed. What we haven't talked about is the center of your data and the different ways that we can measure that, and how far spread out your data is and the different ways we can measure that. So there are 3 different ways that we can measure the center of a data distribution, and they're going to be something that you've heard about before. They're mean, median, and mode. Okay, so what you may not have seen before is the symbols that we use to stand for those 3 things. So it depends on if we are dealing with a sample or a population, but when we talk about the mean, you could see 2 different symbols. If it is a sample, you will see this symbol right here, and we call that X bar. If you are getting the mean from a population, you will see this Greek symbol. It looks sort of like a U with a tail, and we call that mu. Okay? When I talk about the median, you're going to see me use a capital M, and then unfortunately the mode doesn't really have its own symbol, probably because we don't talk about it as much as we talk about the other 2. Okay? But let's get started. So have you ever noticed that bags of chips seem to contain lots of air and not enough chips? So a group of chip enthusiasts from Kitchen Cabinet Kings collected data on the percent of air in each of 14 popular brands of chips. Here are their data along with the dot plot. Okay, so the first thing I want to identify is whether I'm looking at sample data or population data. And in this case, I happen to be dealing with a sample, and I know that because I only have information from 14 different brands of chips. I know that there are many, many more brands than that. This is just a sample to give us an idea of what's happening. So how do I find the median? Well, I start by lining up my numbers from least to greatest. So 19 would come first, and then let's see, 28 and 34 would go next. And then we've got 240, or let's see, nope, we got a 39 and 241s. So those are now marked out. And then we've got a 46, 47, 48, 49. So those are gone. 250s. Oops. And a 59. Okay, so here's our data. So if you remember from the past, the median is just the middle number. So something that helps me is I will start crossing things out. So I'll cross out first, last, first, last, first, last, until I get to the middle. What's my middle number? It's 46. So my median is 46. Okay? Let me erase this so I got a little more room. We can also find the mean. What's the mean? The mean is just another word for the average. And so when I find the mean, I'm going to use my X bar symbol because this data is coming from a symbol. And the way that I find the mean is by adding all these numbers together. Okay, so I start there and I get 596. And no, I am not that good. I typed these numbers in my calculator before I started. Okay, then I have to divide by how many numbers there are. Well, they told us in the problem there are 14 different chip brands here. So I'm going to divide by 14, and I'm going to have to round a little bit, but the mean is approximately 42.57. So if you notice here, let's compare it to our median. Our median was 46. Our mean was 42.57, right? So here's the thing. They are close. They are not exactly the same. So then the question is, which one do you think is better? Okay, well, let's go and let's look at the graph and let's look at what you think is more accurate. So 46 looks like is somewhere right in here. 42.57 would be somewhere down over in here. Which one do you think would be more accurate? I would have to say that the median is more typical, and here's why. Okay? This number right down here is what we call an outlier. Okay, and an outlier is just a number that doesn't fit the profile of all the other numbers. So maybe you had one bag of chips, maybe it's the Dollar General brand, and they shortchanged you, or maybe it was the really expensive brand, and they gave you a whole bunch of chips and not a lot of air. But either way, it wasn't typical of the other brand of chips. And so what happened is when you included that outlier in your data, it caused your average to be either much higher or much lower than it would have been if that brand hadn't been included in your sample. Okay? So what happens is when you have an outlier, it doesn't really affect your median, because median is just lining up numbers from least to greatest and finding the middle. However, an outlier can greatly affect your mean. Okay? So when we have an outlier, we are going to choose to use the median as our measure of center. If we don't have an outlier, we don't have to worry about anything being messed up, and so we are going to use our mean or our average to represent the center of our distribution. So here's what I can learn by looking at the mean versus the median. So if you notice that your mean happens to be significantly less than your median, that is a good indication that you had a low outlier, or maybe you had multiple low outliers. And this is going to cause the overall graph to be skewed to the left. Okay, and remember, when we talk about skewed to the left, what we mean is that we have a tail, or we have extreme values on the left side of the graph. If you notice that your mean and your median are equal, or at the very least they're very close, you probably have a symmetric data distribution. Okay, meaning data is pretty evenly distributed on both sides. If you notice your mean is greater than your median, you probably have high outliers, and so then your graph would be skewed to the right. Okay, I have included some calculator buttons at the bottom of this page that show you how to find the mean and median with some calculator buttons instead of having to do it by hand, if you would like to look at those. I'm not going to go over those right now because I'm going to do a separate video specifically for calculator instructions later. Okay, so moving on to our next section. So we've talked about center. Let's talk about spread. So when I talk about the spread of a graph or the spread of a set of data, what I am talking about is how far apart are those data points spread out. So when I look at these two graphs here for Denver and San Francisco, what do I notice is the same about their high temperatures? Well, the center of that data is right around 65 for both graphs, right? However, what is different is the extreme values. So Denver's high temperature was all the way down near 44 degrees, and it had a high near, looks like maybe around 90. San Francisco's data is more clustered together, so its spread would be smaller. It only goes from 60 to 71. And we have lots of different ways that we can assign a number to the spread of the data, and one of those ways is with range. And the way that we find the range of a data set is by taking the maximum number minus the minimum number. So for Denver, I took the maximum, which is 89, minus the minimum, which is 44, and I got a range of 45. For San Francisco, their maximum was 71. And their low was 60. Well, 71 minus 60 is 11. So you can see the huge difference there on number 2 in the range for those two cities. So another way that we can measure variability or the spread in a data set is using something called standard deviation. And the standard deviation it's about the average distance of the values from the mean. Okay, and so what I'm going to do is I'm going to walk you through how you would find standard deviation by hand. I'll be honest with you, it takes a minute to do it by hand, and so I will also in a later video show you how to get it with your calculator so that you don't have to do this by hand every time. So our symbol for standard deviation, again, depends on if we are dealing with a sample or a population. If we are dealing with a sample, we are going to use a lowercase s to stand for standard deviation. If we are dealing with a population, we are going to use the Greek letter sigma, and I will do my best to draw this, but I am not very good at it. But it looks like that, okay? All right, so if I wanted the standard deviation for Denver, the first thing I would do is calculate the mean of my data. Well, you can kind of tell by looking at the graph, but you could also do it with a calculator. The mean of these 1, 2, 3, 4, 5, 6 numbers right here is 65. And then what I'm going to do is I'm going to take each individual data point and figure out how far away it is from 65. So 44 minus 65 tells me that on the first day, I was 21 degrees below average. Okay? The second day, 51 minus 65, I was only 14 degrees below average. The third day, I was 4 degrees below average. The fourth day, I was right on the money. The fifth day, I was 15 degrees above average. And on the last day, 24 degrees above average. Then what I'm going to do with each of those numbers is I am going to square them. So negative 21 squared is 441. Negative 14 squared is 196, and so on. So just to recap, I found the distance of each data point from the mean. Then I squared those numbers. Then I add all of these numbers together to get a total of 1454. Okay? And then lastly, I'm going to divide 1454 by 6. And the reason I'm dividing it by 6 is because I'm taking an average. I added together 6 numbers to get 1454. So 1454 divided by 6 is 242.3. Okay? And then lastly, I'm going to square root that number, which gives me my final standard deviation. Okay, so again, that takes a long time to do by hand. I don't expect you to do it by hand on a regular basis. I will show you how to do it with a calculator. In fact, that's what I did right here. Okay, but we will get that with the calculator later. Okay, here's what I want you to take away from this. Let's say you added one more day to this data set, and it was a very, very cold day with a high temperature of only 7 degrees. What would happen if you were to add this value to the data set? So first of all, think about your mean and your median. If you suddenly introduce a day that is an outlier, it's very different from all the other days, your mean is going to drop significantly because your mean is the average. So if you're averaging the number 7 in with all these higher numbers, all of a sudden your average temperature is going to drop. However, you'll notice it doesn't change your median very much, right? Because the median is just finding the middle number. So all you're going to do if you add the number 7 into this data set is add 7 to the beginning and then find the middle number. So it's not going to change significantly. Okay? What does it do to your standard deviation? Well, your standard deviation was 17.05. Right? And remember, standard deviation is a measure of the average distance from the mean. Well, if you throw in the number 7, 7 is going to be really, really far away from your average. So now your standard deviation is going to increase. Okay? So let's go ahead and go to the next example. So a couple of notes here. For symmetric data, you are going to use the mean and the standard deviation. And let's remind ourselves of why that is. If you have outliers, your graph is not going to be symmetric, it's going to be skewed. Well, those outliers are going to either inflate or deflate your average farther than it should. It's not going to give you an average that is representative of most people. So therefore, the mean may not be accurate. Right? Well, the way we find the standard deviation, step 1 of that is using the mean. So if the mean is not accurate, the standard deviation will also not be accurate. Okay? So it is only for symmetric data that we use the mean and the standard deviation. For data distributions that are skewed or that have outliers, we use the median because the median is not heavily impacted by outliers. And then instead of using standard deviation, we use something called IQR, and I haven't taught you that yet. We will learn that in the next section. Okay? So just a quick example. If I was asked to calculate the mean rainfall for the cities shown in this table, I first of all would use the symbol X bar, because this is just a sample of 9 cities from the U.S. So X bar is the symbol for sample mean. How would I get the mean? I would add together all of these numbers, and then I would divide by 9 because there are 9 cities. The median would come from finding the middle number, and these numbers are already in order for me. So if I just start crossing out first and last until I get to the middle, I see that my middle number is 40.5, so therefore that is my median. Okay? So then the next question is, would you choose to use the mean or the median to summarize the typical annual rainfall for a U.S. city? Well, when I look at the picture of this histogram that's shown to the right of the table, that is very clearly not a symmetric graph. It is skewed. So kind of imagine there's a tail over here. So that tells me that my mean may not be accurate. I may have some outliers that cause my mean to deflate, right? And so since my mean may not be as accurate as I would like it to be, I'm going to use the median. Okay? And then lastly, question number 4, the standard deviation for these cities, they've already calculated for us, is 15.52. What does this mean? Well, this tells me that the annual rainfall for a city typically varies by 15.52 inches from the mean of 34.94 inches. So what that means, if you think about it, on your graph, here's your mean. Your mean is right here around 35. Most annual rainfall is going to be within 15.5 inches of that. So it's going to be between about 50 inches and roughly just below 20 inches. And if you look at that, that is kind of where your data is clustered, right? So that makes sense. Okay, one last thing that I did want to mention that is not explicitly covered in these notes is the mode. So the mode is something that some data sets have. Some data sets do not have a mode, and that's why we don't talk about it all the time. The data set that we're looking at right here does not have a mode. The mode is the number that repeats most often. So if no numbers repeat, you don't have a mode. However, if we go back to our previous data set, let's see, and that would have been on our previous notes. Let me find it. Where did that go? Let's go back to 3.1. Yeah. Okay, if I go back to this data set, I actually do have some numbers that repeat, and I have a couple of them. 50 repeats and 41 repeats. So both of those numbers would be considered modes. Okay, so you can have no mode, you can have one mode, you can have multiple modes, just depends on the data set. Alrighty. So moving on to our last set of notes for Unit 3, Section 3.4 and 3.5. Okay, so let's talk about percentile for just a minute. What does percentile mean? So if I tell you that you are in the 25th percentile for height, that means that you are taller than 25% of people. So on question number 1, it gives us a data set, and it says Biff scored a 65 on his test. What is Biff's percentile? So if I look at where 65 is, Biff would have fallen right here. So he did at least as well as 3 people in the class. Well, since there are 20 people in this class, 3 out of 20 is 15%. So he did at least as well as 15% of the people in the class, so he is in the 15th percentile. Okay? So our next question is, was Biff above or below the mean? And by how many points? So let's see, our mean was 80, and we know this because it tells us that. So if our mean is 80 and Biff scored a 65, we know that he was below the average How much below the average was he? He was 15 points below the average. Okay? And here's the part that you may have never heard before. By how many standard deviations is he below the mean? Well, our standard deviation is 10. And again, I know that because it tells me in the problem. Okay? So if Biff is 15 points below the mean and one standard deviation is 10 points below the mean, then 15 divided by 10 gives me 1.5. So Biff is 1.5 standard deviations below the mean. This is what is called Biff's z-score. So what we are talking about in this section is a z-score, and a z-score is how far above or below the mean you are. Okay? So here's what the z-score is used for. So we can compare Biff's z-score to Marty's z-score. So Marty scored a 97. What is Marty's percentile? Well, Marty was in the 95th percentile. If we calculate Marty's z-score, Marty was 17 points above average. Or we could say he was 1.7 standard deviations above the mean. Okay? So z-scores allow us to compare how far apart two people were on a scaled score. So you will see this a lot of the times. You may have recently taken an ACT, right, or an SAT. Z-score is something that is calculated to help the makers of the test or to help you know where you stand. Okay? So if we write a formula for calculating a z-score, here's what it looks like. To find a z-score, we start by finding the mean. And we could use the Greek letter mu or the symbol x bar to stand for the mean. If we use mu, it means we have population data. If we use x bar, it means we have sample data. Then what we are going to do is we are going to see how far away we were from the mean. And so this x right here is your number. So if I took a test, that's where I would put my test score. So I would put my test score minus the average, and then I'm going to divide by the standard deviation. And again, we have two different symbols for that. If I use the Greek letter sigma, that means I have population data. If I divide by the letter S, that means I have sample data. Okay, and that will give me my z-score. And what you're doing is you're comparing how far you are from the average to how far everybody else is from the average. That's what a z-score is. So example 6, Goldie scored a 93 on the Unit 1 test. Find and interpret her z-score. So the first thing we're going to do is locate the average. The average was 80. Okay? Then we are going to plug in Goldie's score to see how far away from the average she was. Well, she scored a 93. That means she was 13 points above average. Okay? We are going to compare that 13 to how far away from the average everyone else was. Well, on average, everyone else was within 10 points of the mean. So 13 divided by 10 is 1.3. Goldie fell 1.3 standard deviations above the mean, and that is her z-score. Okay? So we are going to skip example 7. And just a couple of notes here. Z-scores do what's called standardizing a distribution. So one of the things that they are good for is comparing two people's score on different tests. So let's say you took the ACT and someone else took the SAT. What we could do is, because those are scored on very different scales, we could give you both a z-score and then actually compare your z-score to get an idea of who actually did better. Okay? So we are going to skip numbers 1 and 2 here, but I want you to look at number 3. Number 3 says Michigan has a standardized score of 0.267. So when they use this word standardized score, they are saying, hey, Michigan's z-score is 0.267, which means they are slightly above average because their z-score is positive. How many public colleges does Michigan have? So what I am going to do is I am going to use my z-score formula, which is right here, and I'm going to plug in 0.267 as my z-score. Okay, what else do I know? I know that the average number of public colleges in a state is 39.24. So I can plug that in for the mean. I am also given the standard deviation for the number of public colleges in each state. That is 32.844. And then what I can do is I can work backwards to actually figure out how many public colleges Michigan must have had in order to give them a z-score of 0.267. So in order to solve this equation, I need to get x by itself. And so I would start by multiplying each side by 32.844. Okay? And so on the right side, 32.844 cancels. On the left side, 32.844 times 0.67 is 8.769. Well, now I only have one step to get x by itself, and that's to add 39.24 to both sides. And when I do that, I get 48.009. So what that tells me is that in order to get a z-score of 0.267, Michigan must have had about 48 colleges. Okay? All right, so we are going to go back and let's see here, talk about the median for just a second. So let's say that you want another way other than the z-score to compare yourself to other students in the class. What can you do? Well, one thing you can do is instead of finding the mean, which we used for the z-score, you can find the median. So I'm not going to bore you by finding the median by hand right now, but if you find the median height for all of these numbers right here, you find out that the median is 63, okay? What you can do from that point to kind of get an idea of how the data is spread out is the median is the middle. You can then split your data into quarters. So what I have done here is I have listed all 21 numbers that they gave me. We said the median was 63, okay? So the median would have fallen right here. Let me get my pen. The median would have been right here between 62 and, let's see, nope, the median would have been 63. Okay, what you can do is then you can take these numbers that fall before the median and split them in half, and that is Q1. That is the first quarter of your data. So Q1, if I split this first half of the data in half, is 61.5. Okay, then if I look at the second half of the data and I split it in half, that falls between 65 and 68. That is 66.5. Okay, so what I've done is I've split my data into 4 pieces. The middle was at 63. The first quarter of the numbers fell at or below 61.5. The third quarter of numbers fell at 66.5. And then I can give you your max and your min. This is what is called your 5-number summary, and it also gives you an idea of how far your data is spread out, okay? And one of the main things we do with the 5-number summary is we draw what's called a box and whisker plot. And each line on this box and whisker plot represents one of these 5 numbers that I have circled. So the first line that you will draw is your minimum, which is 57. The next line you'll draw is your maximum, which is 77. Those 2 marks right there represent your whiskers. They show you how far out your data goes. And it kind of also will give you an idea of if you have any outliers or not. Okay? These 2 inside lines that make up the side of your box, that is Q1, which is 61.5, and Q3, which is 63.5. And then inside your box, you add one final line, and that line is your median, which was 63. Okay? So using your 5-number summary or your box plot, depending on which one you are given, you can find what is called the interquartile range. So if you remember, I mentioned something called IQR earlier. That stands for interquartile range. So if we think we might have outliers, we might choose to use the interquartile range instead of the standard deviation. Okay? And so how do I find interquartile range? I take Q3 minus Q1. So if I look at my data Q3 was 66.5. Q1 was 61.5. If I subtract that, that is 5. Okay, and so I made a little note over here. Your IQR is just the distance between the sides of your box. So it's how far spread out the people in the middle were. So you're actually looking at the people who were kind of average in your group. Okay? Box plots and 5-number summaries are also good for showing us if we have outliers. And here's the thing, for something to be an outlier, it can't just be a little bit bigger than everybody else or a little bit smaller than everybody else. There has to be a huge gap, okay? So we have a formula that helps us figure this out. If we think that we have a outlier that is too small, we can use the formula Q1 minus 1.5 times IQR. So I'm going to plug in 61.5 for Q1, and I'm going to plug in 5 for my IQR. So if in my calculator I plug in 61.5 minus 1.5 times 5, I get 54. What that is telling me is any number that is smaller than 54 is an outlier. Well, I don't have any numbers smaller than 54, so I don't have any low outliers. If I think that I have an outlier that is too big, I use the formula Q3 plus 1.5 times the IQR. So I'm going to plug in 66.5 for Q3 and 5 for the IQR. And in my calculator, when I type in 66.5 plus 1.5 times 5, I get 74. So any numbers bigger than 74 are outliers. So when I look at my data, I actually do have a number bigger than 74. It's 77. So 77 would be considered an outlier. And I could kind of tell that by looking at my box plot, because look how long this whisker is. So most of your data is down here, and then you have this really long gap between your box and that next whisker. So that was kind of an indication this box plot was skewed to the right. So that was kind of an indication that I was going to have a high outlier. Okay? So question number 6. Ashmita is 63 inches tall. How does her height compare with the other AP Stat students in her class? So here's what I notice. The number 63 is something that we already talked about in this data set. 63 was our median. So because Ashmita's height happens to fall right on the median, that means she is dead center in this class. She's taller than half the class, but she's also shorter than about half the class. Okay? Okay, so when I look at these two box plots, if I asked you to describe shape, center, and spread, could you do it? Okay, so let's start with shape. Okay, so the first thing that I want you to know, the distribution of points scored by the University of Michigan, which is our top box plot, is skewed to the right. Why do I say that? Because the right whisker is significantly longer than the left whisker, so it's skewed to the right. Okay? The distribution of points scored by Michigan State is not as skewed. Okay, it's a little bitter when I compare these whiskers, but notice how the median, if this data distribution was perfectly symmetric, that median would be dead center in the box, and it's not. So this distribution for Michigan State is also slightly skewed to the right. So because these distributions are skewed, right, I have to worry about potential outliers. I have to worry about my mean not being an accurate representation of the population at large. So when I'm talking about the center of my distribution, I am going to talk about the median, not the mean, because I can't be sure that the mean is accurate. So the median is this line right here. And it looks like the median for both teams is about 25 points. Okay? Neither graph shows any obvious outliers. However, the University of Michigan shows lower variability, meaning it's not as spread out. And I can tell that for two reasons. If I look at this box, my IQR is lower. Okay? And also, so let me circle this other box. You can tell the IQR is lower. And also, if I looked at the range, the difference between the min and the max for University of Michigan is much smaller than it is for Michigan State. Okay, so we have got one last topic, and then we are done. So let me get back to my notes. Where did it go? Okay. So we can actually use the shape of a distribution to help us figure out some things about that distribution. Okay, so we have two different rules that we are going to talk about. One of them is called the empirical rule. One of them is called Chebyshev's inequality. Okay, that's a mouthful. So here's what you need to know. The empirical rule is used only for symmetric data sets that are bell-shaped. So if I saw a data set that looked like this right here, I could use the empirical rule. Okay? And it doesn't have to be perfect, but it needs to be close. However, if I saw data sets that looked like this or like this, the empirical rule would not work. That's when I would pull out what is called Chebyshev's inequality. Okay? Chebyshev's works for any distribution, no matter the shape. So here's what those two rules help us with. The empirical rule says this: if you have a symmetric, bell-shaped graph, you have what is called the 68, 95, 99.7 rule. So if you see a bell shape, 68% of people will fall within one standard deviation of your mean. 95% of people will fall within two standard deviations of the mean. And 99.7% of people will fall roughly within 3 standard deviations of the mean. So that means, let's say I give a survey to a bunch of people and I graph their results. If I look at that curve and I notice that their results happen to give me a bell-shaped histogram, I can predict that 68% of people are going to be clustered right around the average. And then as I go farther from the average, I expect to see less and less people. So that kind of logically makes sense. Okay? So let's see how that works. Okay. So the distribution of waist circumference for women who are 8 months pregnant is approximately normal. So when I say that the distribution is normal, what I mean is that it's symmetric, so it's not skewed, and it's bell-shaped. Okay? It has a mean of 44 inches and a standard deviation of 4 inches. Okay? And just a reminder, the reason or the significance of them using these two symbols, so mu and sigma, is they are telling us this is population data. They got this information from some kind of census where they went to all women. Okay? So here's what I can do now. I can draw myself a picture. Okay, and I'm actually going to go to the next page because I have myself a bell-shaped curve. So what I'm going to do is I'm going to put 44 dead center on this graph because that was the average waist circumference of women. Well, knowing that my standard deviation was 4, I'm going to go up 4 and down 4 to get my next two lines. So I can predict that 68% of people will fall between 40 and 48 inches of waist circumference. Then I go 4 more inches in each direction. So now I'm 2 standard deviations away from the average, right? So I can predict that 95% of people will fall between 36 and 52 inches. And lastly, if I go 3 standard deviations out, I'm going to get almost everybody. So 99.7% of women would have a waist circumference between 32 inches and 56 inches. Okay? So using this picture, I can answer a few questions. Okay, so it says a waist circumference greater than 52 inches may indicate excess amniotic fluid. What percent of women who are 8 months pregnant may have excess amniotic fluid? So what I'm going to do is I'm going to go find 52 on my bell curve. Okay, 52 is right here. And what I've done is I filled in some percentages. So if I knew that this was 68, that gave me 34% here and 34% here. If I knew that this line right here was 95%, that means 13.5% of people fell here 13.5% of people fell here, and so on. So if I knew that this line right here was 99.7, 2.35% of people had to fall here, 2.35 had to fall here, and then I have 0.15 left on each side. So knowing that, if I want to know what percent of people fall above 52, which is this line right here, well, that's 2.35% plus 0.15%, which is 2.5%. Okay? Let's look at the next question. So the next question is about what percent of women who are 8 months pregnant have a waist circumference between 36 and 40 inches. So I actually already have that filled in. Here's 36, here's 40. 13.5% of people fall in that bracket. And again, I just want to reiterate how I knew that. So 68% of people fell here, right? So that means 34% and 34% in these two sections. 95% fall in this larger section. Well, 95 minus 68 leaves me with 27% to fall here and here. If I split that in half, that's 13.5 in each section. Okay? So lastly, what do we do if we don't have a bell-shaped distribution? We use what is called Chebyshev's inequality. It is not something that you have to have memorized. Okay? Chebyshev's inequality is right here. So the formula is 1 minus 1 over k squared times 100%. And k stands for the number of standard deviations that you fall from the mean. Okay? So here is how that works. So on letter A, it says determine the minimum percentage of students who have IQ scores within 3 standard deviations of the mean according to Chebyshev's inequality. So if I want to be within 3 standard deviations of the mean, that means that k is going to equal 3. So I'm going to plug in, instead of 1 minus 1 over k squared, I'm going to write 1 minus 1 over 3 squared times 100%. Okay? And if you use your calculator to do 1 minus 1 over 3 squared, that gives you 8 ninths, which as a decimal is 0.888, and it keeps going. It's 0.8 repeating. Well, if I multiply that by 100%, that gives me 88.9%. And that's how Chebyshev's inequality works. Okay? So again, Chebyshev's will always work no matter what distribution you have. The problem with it is because you don't know the shape of the distribution, it may not be as accurate. The empirical rule is more accurate, but it doesn't always work. It only works if you have bell-shaped data. All right, and we are done with Unit 3. Please let me know if you have any questions.